line yesterday. On Tuesday, we'll touch it on again. Now tomorrow, okay, we'll be over at E30607, which is the other room over there. Okay, tomorrow we are going to do the exam papers. Okay, we are going to review exam papers. Tomorrow we will focus on the questions that are on the capacitor, inductance, electric field, and magnetic field. But the next Saturday, okay, we will review the exam question, the paper on these propagations, transmission and reflection and transmission line. Okay, I will not give you the solutions because we are not giving up solutions, but I will tell you this how to solve them. Okay, on the during the two remedial sessions this Saturday and next Saturday. Next Tuesday we will finish off transmission line and do revisions. Alright, and next Friday we will do tutorial 8 and we review CA2. Okay, just like we have reviewed CA1 prior to your CA1. Okay, but unfortunately I don't know why you still don't do well. But never mind, we'll still review CA2. Okay? We'll still review CA2. Now then on the last week, which is week 13, okay, we will review CA2, week 13 Tuesday is CA2, okay, at 2:30 to 3:30, okay, at this EA, okay, at EA, and after that we don't have any class, alright. The next Friday, okay, we will review CA2 2017 and we will do a final revisions, okay, and after that, well, good luck to all of you. And of course, I also have office hours. Okay, I also have office hours. Correct. Okay, and this one again is already on IPLE. Okay, please drop in. Okay, on all those time. Okay, during all those time. Now, from now to the exam times, okay, during this office hour is already on IPLE. There's no need to take the program. These are the times which you do not need to make any appointment. Okay, you don't need to make any appointment in order to see me. But from now until that time, okay, if you want to see me, please make an appointment. Hey, why the thing is missing? Okay, the dates are missing. Alright, the dates are missing. Now, until those dates, okay, if you want to see me, please send me an email to make an appointment. Okay, I'm available. Okay, most of the time when I'm not attending meetings or teaching classes, and if it's necessary, okay, I'll be around Saturday and Sunday as well. Okay, Saturday morning is our remedial classes. Saturday afternoon from 2 to 5 now. Sunday I'm around here also. Alright, so if you really need to see me weekend, in the big class, okay, you can send me an email around Saturday, Sunday. Alright, no issue. Okay? Now, before we do our tutorial 7, alright, gentlemen. Alright, what's that? Sorry? Tutorial 8, what? Wait until you have time first. I mean, no, we are running out of time. I know, but on the last day, see whether they have time. I think I know that. Okay, okay. Basically, beside 4 missing in actions, mostly all of you are doing well. Okay, the person who is not doing well, I've already sent an email to him already. Okay, the rest are doing well. 2 persons or those I give you full marks. There are a lot of things which you got them wrong, which okay, never mind, I'll tell you what has these 2 persons got it wrong. So if you are the 2 persons, please aware of it later on. Alright, but I still need to correct. Now, a plane wave traveling in a dielectric with a relative dielectric constant is equal to 9 is incident upon the second media. So this is epsilon I equal to 9, this is epsilon I equal to 4. Alright, now we are asked to find the refraction coefficients, transmission coefficient, and what are the ET. What is ET? ET bigger than EI or smaller than EI? Now, refraction coefficient is very easy. Gamma equal to zeta 2 minus zeta 1 over zeta 2 plus zeta 1. And what are the answers down here? First thing, you straight away can eliminate 3 and 4. Why? Can somebody tell me why I can eliminate answer 3 and 4 straight away? Come on, come on, come on. Why you can eliminate answer 3 and 4 straight away? 1, yes. Refraction coefficient is always less than 1. Look at this. How can this one be bigger than 1? This is a difference, this is the sum. So 3 and 4 are out straight away. And 1 and 2, since they are the same answer, except one positive and one negative, all you have to do is to decide which is whether it's positive or negative. You don't even have to calculate. Now, what is zeta? Remember I said zeta is equal to this, which is equal to 120 pi divided by square root of epsilon r. This guy epsilon r is 9, this guy epsilon r is 4. You divide by square root 9 and divide by square root 4, which is bigger? This is smaller. Alright, when divided by a bigger number, it is smaller. So this zeta 1 is smaller than zeta 2. Zeta 1 is smaller than zeta 2, that means it is positive. Why count? We don't have to calculate. You eliminate these two, then what? Positive or negative? Positive. Okay. Done. Then, transmission coefficient, do we have to calculate? No. Because 1 plus gamma is equal to 4. Since I know gamma is equal to 0.2, 1 plus 0.2 equals 1.2. What do you have to count? 10 seconds you got the answer. And if 4 is greater than 1, that means ET is greater than EI. If in 10 seconds you got the answer. What's that to calculate? Right? Make sure that you know the concept well. Gamma must be less than 1, so when you do your calculation, when you do the exam, if you get a gamma greater than 1, die already, something is wrong. Okay, don't do that. Alright, so you got all this properly. Now, what is the difference? What are the mistakes that committed by the two of them? One is gamma is equal to 120 pi. Hey, where you get the equation from? You multiply by square root of epsilon r. One of you, I don't know who. I mean, if you have done that, own out yourself. Okay, another one is, pi missing. Where's the pi gone to? Alright, don't make careless mistakes like this, alright, in the exam. But somehow, the answer is still correct. I don't know whether after all your calculation, you still got the correct answer. I'm not sure how you got that, but never mind. Alright, okay, I let you have the give you benefit of doubt. Alright? But don't make careless mistakes like this. Don't miss out the pi. Don't bring the square root epsilon r out. Alright? In the exam, this is going to cost you a lot of marks. Okay? Alright, let's go to problem 7. In fact, just now, if I want to really be nasty, okay, instead of 9 and 4, which you can take square root very easily, I get 901 and 809. So you take square root and then you calculate the log. But there's no need to do any calculation. You look at it, eliminate whether plus, whether it's bigger or smaller, you get the answer straight away. Alright. Tutorial 7. A uniform plane wave. I forgot my copy. A uniform plane wave in air with EIZ equal to polarizations, x directions, propagation directions, z directions, propagation constant 6. Okay, it's incident normally on a surface at z equal to 0, the medium having a direction constant of 2.56 and relative permeability equal to 0.1. So this is air. This is epsilon r equal to 2.56. Alright, so EI is equal to x, then E minus J sig Z. Incident, reflection, transmissions. Very simple. Find the following. Instantaneous expression for ER, HR, ET, and ZT. Okay, let's find the phasor first. Okay, let's find the phasor first. Remember, your ER, what is your ER? What is your ER? It's also X. We always assume the same X. Gamma tan E plus J sig Z. Right? Now to solve these kind of questions, okay, I want you to write down, before you solve the questions, you write down everything. You write beta 1 equal to 6. Zeta 1 is equal to 120 pi. Alright, this is 1. This is 2. K1 is equal to 6. Okay, then zeta 2 is equal to 120 pi divided by square root of 2.56 equal to whatever. You get the value. Okay, then what is A beta already? Beta, okay, then what is beta 2? 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 Beta equal to what? Remember, V is equal to omega K or omega beta. Beta is equal to omega over V. Right? Am I correct? Now omega is the same. V not the same. Am I correct? Only the velocity not the same, because the velocity down here, this is equal to omega over C. This is the air. Air, the velocity of propagation is equal to C. Now, down here, beta is still equal to the same omega, but the velocity now, remember the velocity in a dielectric is slower. It's C divided by square root of 2.56. So it is equal to square root of 2.56 omega C equal to 6 times square root of 2.56. Right? Am I correct? Okay, so you got beta, you got zeta. Why you have to write this one down? Because after that you have to write the propagation constant, and then you have to write the reflection coefficients and transmission coefficient. You need the zeta. Alright. So once you got this one here already, then your gamma, the reflection coefficient, equal to zeta 2 minus zeta 1 over zeta 2 plus zeta 1, which is equal to, I don't calculate,
beta, this is equal to 1 minus square root of 2.56 over 1 plus square root of 2.56 is equal to minus something. You can calculate it out. Why I can write like this straight away? Because this guy divided square root of 2.56, I just multiply 2 out. You can you see or not? 120 pi divided by square root of 2.56 minus 120 pi. 120 pi divided by 2.56 plus 120 pi. So I cancel off all the 120 pi. What I left is 1 over square root of 2.56 minus 1 over 1 over square root of 2.56 plus 1. So I multiply top and bottom by square root of 2.56 is equal to 1 minus this, 1 plus this. So you're quick enough, you can see it. I mean, well, always calculate. If everything calculate, there are so many errors, don't need calculate, just come back. So you got the reflections coefficients. And you need your transmission coefficient, same thing. Do you want to calculate? Don't calculate. If you still want to calculate this one, no point, because this is 1 plus gamma. Why calculate that one? You know it's 1 plus gamma. Once you calculate gamma, you do. But of course, if you recalculate, there is an advantage. Is that if you make a mistakes in pressing your calculator, the error propagates to here. Okay, you just put 1 plus gamma. So maybe it's good for you to recalculate also, and then you check that it is equal to 1 plus gamma to recheck your answer. That is also good. Okay, so sometimes you waste a lot of time, does not mean that it's no good. Alright? You just straight away write 1 plus gamma, it is very fast. But on the other hand, if your gamma calculated wrongly, your 1 plus gamma also wrong, then everything also wrong. Okay? Now, so this is my ER. So what is my ET? ET is also equal to X, or then E minus J 6 square root of 2.56 Z. This is B beta 2 now. Beta 2 now. In the second, in medium 2 is now beta 2. So far, any questions? Everything alright, yeah? So now once you got this, the magnetic field is very simple. Hey, what is gamma? What is gamma? Can you put in the value? What is gamma? Minus 0.231, yeah, it's minus, okay? You can see it's minus, right? Because 1 is definitely smaller than square root of 2.56, okay? So it's minus 0.231, and this one is equal to 0.769. Alright? So now it's equal to ER is equal to minus X. 0.231, that means 2.31. Alright, so this is equal to 7.69. And what is beta? The beta value? Beta value is 9.6. I don't even calculate omega. I didn't even calculate omega. Because there is no need to calculate omega. There is no even necessity to calculate omega. A lot of time there are a lot of calculations are not needed. Now, okay, once you got E, you got R, you got ER, ET. The next thing is, of course, you get all the instantaneous expressions, right? Instantaneous expressions. Oh, sorry, you want H first. Okay, so what is HR? What is HR? There are two ways to do it. Alright, one way is of course the official way, h is equal to 1 over zeta k cross E. Alright, but another way is of course, because this is not a complicated scenario, k is not pointing in the funny directions, E is not in the funny direction. It is besides actually very simple. If electric field is propagating in the minus x directions, x, y, z, let's say x, y, z. If the electric field is propagating in the negative x direction, if the electric field is polarized in the minus x direction, and it is propagating in the minus z directions, where is the magnetic field supposed to be? Y, right? Or one way, another way to do this is that, okay, what is my HI? What is my HI? If do this, it is easier to see. What is my HI? Polarizing X, propagating Z, X, Y, Z, E, H, K. So this one must be Y. Correct? This one must be Y, then zeta 1E minus J6Z. Okay? This one must be Y. Because E cross H equal to K. X cross Y equal to K. And the next thing that we see that, hey, remember I said before, if the X change directions, Y does not change. Okay. If the X change directions, Y does not change. If the X does not change direction, Y must change. Okay, for incident and reflected. So this is equal to 2.31 divided by zeta 1 E plus J Z. And this is HT. This one in the same direction, so it is Y 7.69 divided by zeta 2. Okay, so you see zeta 1, zeta 2, all these are needed over here. And that's it. Now, writing the phasor form to instantaneous form in such a simple manner, I don't think I need to go through, right? This is basically just here and become, you put a j omega t, become cosine omega t. This one here become E Z T is equal to minus x 2.31 cosine omega t plus 6z. Alright, this is just like that. Okay, or if you want to bring the minus sign in, it's also very simple. Bring the minus sign in, cosine become plus pi. You just add the phase angle plus pi. Alright, this sign here, sometimes they don't write the sign here, sometimes they write the sign inside here to represent as a phase angle of pi to represent the minus sign. That's also okay. Alright, so the rest are very simple. Okay, I'll just leave it to you to look through. Expression for the time average Poynting vector of E cross H conjugate. You see, when you look at the way of the tutorial, okay, you have a glimpse of what kind of questions they're going to come out in the exam. Because the exam questions, the framework is still not far away from the tutorial. Okay, not far away from the tutorial. You just look at the framework. And the best thing to look at the partial questions. Okay, and that's the reason why tomorrow and the next Saturday we're going to look at the partial question, so you get a glimpse of what kind of things you are going to expect. Now, so what is a Poynting vector? That one I don't want to do because this one very straightforward. Okay. Now, once you got that, okay, once you got that, got all this. Okay, the phasor form, the instantaneous form. Now, all this, okay, it is not expected from you. Okay, I don't think you need to derive from here E1 cross H1 conjugate and then do down all this. Okay, what is expected from you if you ask this one will be from here onward. EI naught squared over 2 zeta 1 minus ER naught squared over 2 zeta 2 is equal to, which is equal to 1 minus gamma squared EI naught squared over 2 zeta 1. Will be just equal to this. Okay, will be just equal to this. And the transmitted pointing vector will be just equal to this. It is not squared divided by 2 zeta 2. Of course, then you have to add the directions of propagations. Okay, you have to add the direction of propagation. But once again, I repeat, okay, this part here, okay, is not required from you. Alright, you just need to use that expressions which is derived in the lecture. Alright, which is derived in the lecture, and that will be alright. Any questions for question number 1? Any questions? Okay, no questions. If you have questions, you better ask. Don't wait until too late. Alright. A uniform plane wave in air is partially reflected from the surface of a lossless material whose intrinsic impedance zeta unknown is unknown. Okay, zeta here is unknown. A measurement of the electric field in front of the interface use a 15-meter spacing between successive minima, with the first minimum occurring at 0.75 meter from the interface. A standing ratio of 5 is measured. What is zeta mu? Alright, at the interface. Okay, at the interface here, I have a standing wave. Alright, they say that this is zeta 1, this is zeta mu. Alright? Now, what are the things that they know? Successive minima is 1.5 meter. Okay, what does it mean now? That means lambda is 3 meter, because remember we said that for standing wave the successive spacing is equal to lambda by 2. This is lambda by 2, so lambda is equal to 3 meter. Okay, we know one thing already. 1 lambda is equal to 3 meter. When lambda is equal to 3 meter, that means k is equal to 2 pi over lambda. We also know. Okay, so I know the propagation constant as well. Okay, what other things do we know? Okay, from that piece of information we know. With the first minimum occurring 0.75 meter from the interface. Okay, that means they say that this is 0.75 meter. Aha. If the minimum is 7.05 meter,
The standing wave cannot look like this. If this is 1.5, middle here should be 0.75, right? This should be 0.75, right? Symmetry, right? So, that means the interface must be here. So this one must be, at the interface there must be a maximum. Alright, must be a maximum. Alright, so that is the standing wave look like. Now, VSWI equal to 5. The next thing is VSWI equal to 5. Now, VSWR is equal to 1 plus gamma, 1 minus gamma. Okay, 5 is equal to 1 plus gamma, 1 minus gamma. So 5 minus 5 gamma is equal to 1 plus gamma. So 6 gamma is equal to 4. Gamma is equal to 2 over 3. Alright, so gamma is equal to 2 over 3. But the question is this gamma is a magnitude, right? The one that to calculate VSWI is magnitude. So if it's magnitude, it can be either, gamma can be either equal to plus and minus 2 over 3. So whether it's plus or minus, can somebody tell me now? Can somebody tell me now what is plus or minus? Plus or minus? The answer is plus. Why? Because the maximum occur here. If the maximum occur here, that means the two vector must be in phase. Okay, the two vector must be in phase. So it must be maximum here. Just when the gamma is equal to zeta 2 minus zeta 1 over zeta 2 plus zeta 1. Alright. Now, gamma must be positive. Okay, gamma must be positive when zeta 2 is greater than zeta 1. Alright. If zeta 2 greater than zeta 1, that means gamma is equal to positive number. Remember? Okay, when zeta 2 and zeta 1 are real. When zeta 2 is smaller than zeta 1, then gamma is equal to negative number. Now, if it's negative number, that means at the interface here, the incident here, EI naught plus gamma EI naught. Okay, this is my ER naught. The incident here, the electric field is EI naught plus gamma EI naught, or EI naught plus ER naught. Now, if gamma is positive, this one of course bigger than EI naught. If gamma is negative, of course it's smaller than EI naught. Alright, so we see that it has a maximum. It has a maximum, that means it's bigger than EI naught. If bigger than EI naught, gamma must be positive. So gamma is positive. This is the value. So we put in here is equal to 2 over 3. And zeta 1 is A, right? 120 pi, 120 pi. Zeta 2 is zeta u. Okay, so you can calculate zeta u. Okay, you can calculate zeta u. So you see, you just extract the information from the question step by step. Okay, extract the information from the question step by step. Alright. First of all, determine from 1.5 here, you know the wavelength. Okay, you know the wavelength. And once you know the wavelength,
you see that, hey, this guy here, half of it is actually a maximum occur at the standing wave. Okay, and if maximum occurring at the standing wave, I know that my gamma is plus or minus. If the maximum, the gamma is plus. If it is minimum at the phase here, then the gamma is negative. So you know that, okay, it will have to be maximum or minimum. But you might want to ask me, hey, why the standing wave must always be maximum and minimum? It always is maximum and minimum provided that zeta 2 and zeta 1 are all real value. Okay, if zeta 2 and zeta 1 are not real value, they are complex number, then the standing wave will be somewhere here in between. Alright. If zeta 2 and zeta 1 are real, okay, because your gamma is equal to zeta 2 minus zeta 1 over zeta 2 plus zeta 1. If zeta 2 and zeta 1 are complex number, then the standing wave will sit somewhere, will hit the interface somewhere in between the maximum and the minimum. But if the zeta 2 and zeta 1 are real, then the standing wave has only two options. Zeta 1 and zeta 2 are real, standing wave has only two options. One is minimum, one is maximum. And zeta 2 less than zeta 1, it is minimum. Zeta 2 bigger than zeta 1, it is maximum. Okay, no other choices. Okay, once you got that, you can calculate the zeta u. Alright, any questions? This is a concepts problem. Okay, this problem make use of your knowledge in the concepts of reflection coefficients and standing wave. This one, question 1, a lot of calculations. Okay, question 2, concepts. Any questions? Any questions? No? Okay, ah? Oh, a long-winded questions. 3, 4. Okay. No issue. Uniform plane wave, if a frequency of 3 GHz travels in the z directions in a lossless medium with epsilon r1 equal to 4, mu r1 equal to 1, electric field polarized in the x directions, wave impinges normally on another lossless medium or region 2, epsilon r equal to 2, epsilon mu 1, mu 2 equal to 1. You see, this kind of thing, lossless, lossless. Okay, lossless, lossless. If there's any standing wave, the standing wave will have to be either maximum or minimum. Okay, whether it's maximum or minimum, you see that epsilon r2 is greater than epsilon r1. That means zeta 2 is smaller than zeta 1. And if zeta 2 is smaller than zeta 1, that means the reflection coefficient is minus. Okay, you see straight away by this one I can do a lot of things. If the reflection coefficient is minus, if reflection coefficient is minus, if there's a standing wave, the standing wave must be a minimum, and the reflection coefficient is minus. What does it mean? Theta equal to 1 plus gamma. If gamma equal to negative, that means my theta is less than 1. So that means my transmitted electric field is smaller than incident electric field. Okay, there are so many things I can deduce from just simple things like that. Alright? The amplitude of incident electric field is 100 volts per meter. Write phasor instantaneous expression for E1, H1, total field, E2, H2, the total field. Draw the standing wave pattern. I say. Okay? Now, actually, this kind of thing, not much concepts. Alright. I just indicated, let's go through the. Okay, now, this is what I advise you to do. Okay,
write down all this. When you do this kind of questions, write down all this. Because, put it this way, if you don't write it down at the end of it, okay, if you give me a wrong answer, it is very hard for us to determine whether you do not know or it is a calculator error. But once you got all these things here, okay, and we see that everything's are correct, the flows are correct, and if the answer is wrong, okay, then we say that, okay, it's wrong, just deduct 2 marks, that's all. Not simple. Okay, so get all these things done, all the preliminary. Okay, omega is given, omega is 3 gigahertz is given. Okay, then epsilon 1 is known, epsilon 2 is known, mu 1 is known, mu 2 is known. Then you can get beta 1, beta 2, zeta 1, zeta 2. You can calculate everything now, and refraction coefficients and transmission coefficients, you get everything now. Now, so this one is very simple. E1, okay, E1 is equal to EI plus ER. EI plus ER, okay, EI plus ER, they share the same EI naught, they share the same EI naught. This is propagating forward in the Z direction, this is propagating backward in the Z directions, and the difference between the amplitude is gamma. Okay, whether gamma is positive or negative is negative down here, but it does not matter. The gamma will take care of it, so it's a good gamma. Alright? So same thing, H. Alright, H same thing, okay. You've got to take care of the sign here. Okay, this sign here is very important. Okay, this sign here is very important because remember, if the electric field don't change sign, then the magnetic field does not. Okay, so you have to take care of this sign here very, very carefully. Now, why is this one written in this way? Now, why is this one written in this way? Now, you see, this is 1 plus gamma. Okay, this is 1 plus gamma. Why is it written in this way? Okay, these questions actually is not a trick questions. Okay, it just want to bring out another specific property of the so-called standing wave. Alright, you see that, okay, if I multiply in, this term is the first term. Okay, this term is the first term. Now, if I multiply in, this term is the second terms. Okay, but if I multiply in gamma E minus J beta 1Z, gamma E minus J beta 1Z, these two terms actually cancel each other. Okay, these two terms actually cancel each other. Alright, but I just add one term here and add one term there. Alright, if I add one term here and add one term there, what is the result? The result is this one, I can write it in terms of the sine functions. Okay, write in terms of sine. Write it as sine. Okay, and this term just retain. Now, how does this one look like now? This one looks like now, you see, in region 1, I have a standing wave, I have an incident wave, then I have a reflected wave. Now, but since the reflected wave is only of a partial power of the incident wave, obviously some of the power will still pass through to become a transmitted wave, right? Alright, so you can see that if you rewrite it this way, I will consist of a still forward propagating wave, but a reduced amplitude. The amplitude originally is 100, now become 80, of a reduced amplitude, so a reduced energy, and with a standing wave portions over here. Okay, this is a standing wave portion. Okay, you do the same thing for cosine, but when we write this one, it's the instantaneous form. How come they never write in it? They only want vector. They only want the. They want instantaneous. How come they never write instantaneous down here?
Okay, the solution is not complete. Huh? Okay, this is the phasor form. Okay, this is the phasor form. Now, how do we write the instantaneous form? Let me write the phasor form down here. E1 Z is equal to X 80 E minus J 40 pi Z minus J 40 sine 40 pi Z. Alright, this is the phasor form. Okay, how to do the instantaneous form? We do the instantaneous form by introducing the EJ omega t, right? We introduce this by EJ omega t. Am I correct? We just put the EJ omega t back in, and then you take the real part. Okay, but before you do that, because there's a J here, okay, there's a J here, I just put EJ pi by 2. Alright, I just put EJ pi by 2, so to replace the J. Now, if I want, I can put the minus there also. How to put the minus? How to take care of minus? You can either have EJ pi or EJ minus pi. You can have either one of these. Alright. So if I take EJ minus pi, it will become E minus J pi by 2. Now, so if I take the instantaneous form, I will become 80 cosine omega t minus 40 pi z. Right, this is the real part of this one. Okay, plus 40 sine 40 pi z, and take the real part of this, cosine omega t minus pi by 2. Okay, so that is the instantaneous form. It wasn't done here. Okay, that is the instantaneous form. Now, what differentiates a propagating wave and a standing wave? Once again, I told you in the lecture, but now I want to emphasize again. For propagating wave, the T and the Z, okay, Z is the direction of propagation. The T and the Z, okay, the T and the direction of propagation must be in the same argument of the cosine terms. The standard is cosine, but sometimes you write sine, alright, but it doesn't matter. It must be a sinusoid. Okay, the T and the propagation must be in the same sinusoid. But for a standing wave, you see they are in different sinusoid. Okay, so you can see that now I have a propagating wave sitting on top of a standing wave. So you can see that I have a propagating wave sitting on top of a standing wave. Alright, so when you do that for the cosine, and once again remind you, when you write down H1 equal to Hi plus HR, make sure that your direction is correct, okay? Make sure that your direction is correct. Alright? Once again. Okay, so once you do that, now E2 is very simple. E2 is just basically a propagating wave. It just have a propagating wave. Okay, E2 It's just a propagating wave. There's no standing wave here. Alright, so if you want to plot, okay, if you plot, it becomes like this. It becomes like this. You see, the electric field is a standing wave, and then by the time you reach here, it becomes the new magnitude inside this one goes through. Magnetic field is like this. Okay, it change. By the time you reach here, it is that magnitude goes through. Okay. Now, why they must have the same magnitude here? They have to be, right? Because the tangential electric field is continuous across. If it's not the same, how can it be? First thing. Second thing, you see, my standing wave minimum is here because why? Because gamma is equal to negative. Why? Because zeta 2 is less than zeta 1. Okay? And you can see that if E is minimum, H is maximum. Alright? Otherwise, no conservation of energy. Same thing, this is minimum, this is maximum, this is minimum, this is maximum. Alright? So there are a lot of things that you can see from here as well. Alright? Now, so where are the maximum and where are the minimum? Actually, you can apply the equations. But in this case here, do you really need to know the equations? Do you really need the equations? No need. Right, no need, because we know, what do we know? We know that the standing wave has to be minimum here. Okay, the wavelength, 3 gigahertz, the wavelength is 10 cm. Okay, the wavelength is 10 cm. So the first maximum is 5 cm away, the next minimum is 10 cm away, then the next minimum is 15 cm away, and lambda, same thing, if this minimum is maximum. So for this kind of case, for zeta 1 and zeta 2 are real case, actually it's very simple. Alright? Because down here it is either maximum or minimum, and then the next one is either, if this one is minimum, the next one is maximum. So there's no phase. Okay, no phase. Only when the refraction coefficient has a phase angle. Remember this one, refraction coefficient, the phase angle is either 0 or pi. That's why I also positive thing. Only when there's a phase angle, then you really need to go to the equation. Alright, then you have to go to the equations and sum all the equation. But actually for this kind of simple thing, equation is not needed at all. Alright, any questions? And by the way, tomorrow is over at room 7. Room 7 is a much smaller room. Okay, so not everybody comes is okay. If everybody comes and you have to squeeze, the room is a smaller room. But I cannot get this room, I don't know why. Alright, any questions before I move on to the last questions? The electric field of a uniform plane wave in a lossless non-magnetic medium. Now, what is mean non-magnetic? Non-magnetic means that mu r equal to 1. Alright, non-magnetic medium equal to mu r equal to 1. Now, if in the exam or in the CA, it never say anything about non-magnetic or magnetic, it is okay for you to assume mu r equal to 1. Okay, because a lot of common material mu are always equal to 1. Okay, characterized by epsilon I to the 16 for z smaller than 0 is given by I. Yeah, this one's a bit troublesome now. So now I have a mu r equal to 1, epsilon I equal to 16. And now my E Z T is equal to tan cosine omega t minus 100 Zx plus 20 cosine omega t minus 100 Z plus pi by 3 y. Okay? The wave is incident on a lossless medium characterized by mu I equal to 12, epsilon I equal to 6. Alright. Find expressions for the instantaneous reflected and transmitted electric field. Find the average power density at Z equal to 8. Now, how to approach this one? To approach this one, okay, this is the, okay, this one is incident, okay, so this is EI. Okay, this is incident, so this is EI. Now to do this, the advice is write it down in phasor form first. Okay, so what is the phasor form first? EI Z is equal to, how to write the phasor form? X, right? Polarization is X. Magnitude is 10. EJ omega t, this part after that we're going to throw away. E minus 100 Z. Okay, right? The first one. Okay, huh? The first one, no problem. We just translate this one to become here. Then the second one is Y 20 EJ omega t, which is going to throw away. E minus 100 Z EJ pi by 3. Well, not difficult. Okay, not difficult. It's not that difficult. And they are, you can see that they are the same wave because they have the same propagation constant. Now, the only thing that we don't know is, we do not know omega. Did they tell me what is the omega? No. They didn't tell me what is omega, so we do not know what is omega first. Okay, but what other things can we do? Can we write down? What is my beta 1? This is equal to 100. Right? My beta 1 is equal to 100. What is my zeta 1? My zeta 1 is equal to square root of mu over epsilon. Mu r is equal to 1, epsilon I equal to 16. So this is equal to 120 pi divided by 4 is equal to 30 pi. Right? Square root of 16 is equal to, this is square root of 16 is equal to 30 pi. Okay, I got this one ready. Remember, write down all these first, write down the reflection coefficient, write down the transmission coefficient. Now, then where is my beta 2? Now, you want to find omega, or you don't find omega, also can. Okay, if you want to find omega, remember, your V is equal to omega over beta. Alright, and what is the velocity? Velocity is equal to c over square root of 16 is equal to c over 4 is equal to omega over beta. So omega is equal to 3 times 10 to the power of 8 divided by 4 times 100 is equal to 75 times 10 to the power of 8. So equal to 7.5 gigahertz. Okay, if you want to find omega, you can find omega. Alright. But if you don't find omega, it's also okay because remember, beta 2 is equal to omega over V2, which is omega over C divided by, this one is a bit troublesome. Okay, this one divided by troublesome is the square root of 12 times 6, 72. So it's equal to 3, 2, 4. Wow, it's not easy. So okay lah, never mind, calculate lah. Okay. Now, so what is your V2? This is V1. What is your V2? V2 is 1 over square root of mu epsilon is equal to 3 times 10 to the power of 8 divided by square root of mu r is 12, epsilon r is 6. What is the number? 72. What is the square root of 72? I don't know. I used to be able to do mental calculations. Now getting old, I cannot do mental calculations already. Don't know what it is. Okay. So beta 2 is equal to 212.13. I mean, I in the old younger time I can do mental calculations, but now old. Okay, so it's 212, right? So this is equal to 212. Alright, so is it okay? So far? Any questions? So far, you write down, remember, before you start to do things, you write down all the omega, beta 1, beta 2, zeta 1, zeta 2, and refraction coefficients. Okay, and zeta 1, zeta 2, and refraction coefficient gamma, and transmission coefficient and all. Okay, so once you got this, zeta 2 is equal to how much? 120 square root 2 pi, 120 square root 2 pi, and then gamma is equal to 0.7, 4 is equal to 1.7. Once again, write all this down, okay? There are marks, alright, and there are marks, and also if you make mistakes, we can deduce from this thing that you do know the answer. It's just basically calculating error by pressing calculator, and that is okay. That is very common to anybody, even to good student. I'm praising myself lah, huh? Because I press a calculator 3 times, I can get 3 different answers. It's very common. So if you see exam standard solution, that's why I don't put out the standard solution. If you put out standard solution, you can see that there are a lot of errors inside there. Okay, so now you got this one already. So what are the things that you need to do? Reflected, transmitted. All right. So what are we going to do? The reflected. ERZ. I write my x. Same. This one multiplied by the reflection coefficient, 0.7. 0.7 times 10 is 7. Okay, I don't need the EJ omega t, alright? So this is E plus, sorry, I missed out the J here. E plus J 100. Alright, so you see that the same thing, same polarization. I don't have to think how will the polarization change or not, because that will be taken care of by the refraction coefficients. Refraction coefficient is 0.7 times 10 becomes 7. This one for propagating wave, reverse propagating wave. Okay? Then the next one, next component, y, 20. X and y both tangential to z. 20 times 0.7 is equal to what? 14. 14 E plus J 100 Z. This one remains. No problem. And once you have written this one, I presume that you can write the instantaneous form very easily. Okay, then the transmitted field, ER, X is still the same, 1.7 times 10 becomes 17, E minus J Now is 212. 212Z. Beta 2 now. And then the second component, Y. 20 times 1.7 is 34. E minus J212Z EJ pi by 3. Alright, then after that we change it to instantaneous form. I think how to convert this to instantaneous form is actually no sweat. Shouldn't be any issues to you now. Okay, after doing so many times. Sorry, is anything wrong? Because the magnitude is the incident magnitude multiplied by reflection coefficient. Incident magnitude multiplied by reflection coefficients. Alright? Okay? You can see that the polarization is the same. Polarization is the same. We keep the same polarization. Magnitude reflected field is the incident electric field multiplied by reflection coefficients. Magnitude multiplied by reflection coefficients. Forward propagating wave, change to backward propagating wave. Forward propagating wave, change to backward propagating wave. The phase, keep that. Alright, then down here, polarization is the same. Incident field multiplied by transmission coefficients. Now, still forward propagating, but beta 1 changed to beta 2. This component is still the same. Magnitude multiplied by reflection coefficients. Change to beta 2, still forward propagating. So everything is the same. Now, then the next thing is do H. Okay, then the next thing is do H. Now, when you do H, I give you one for example. I just do this one. What is my HRZ? HIZ, we do HIZ first, alright? We do HIZ first. Easier to see. HIZ first. X, propagation is Z, X, Y, Z, right? So this one should be Y. This is 10 divided by, what is theta 1? 30 pi. Alright? So E minus J 100 Z. That's the first component. The second component, when E is polarizing in the Y directions, but need to propagate in the Z direction. What is the H supposed to be? H supposed to be in the minus X. Alright? So this one should be in the minus X. 20 over 30 pi E minus J 100 Z E J I by 3. Because Y cross X is equal to minus Z. Y cross minus X equals to plus Z. Alright? Now, so once you got this, then what is my HR? Same thing, if you want, you can go and make use of this one. But if not, you can simply write down, okay, polarizations. Okay, polarizations. EI to ER. If the electric field did not change directions, the magnetic field must change directions. So this is minus Y. Okay, minus Y. Then what?
7 over 30 pi, because E and H is always related by the zeta. Okay, 67 over 30 pi. So E plus J 100Z electric field didn't change direction, so magnetic field must change, so it's plus X 14 over 30 pi E plus J 100 Z E J pi by 3.
So you see that you can either use your equations or use a simple rule that if the electric field changed polarization, the magnetic field won't change. If the electric field didn't change, the magnetic field must change. Because probably you do not know that, because we never show you, is that the actually we don't show you is because we do not want to confuse you. Is that actually the gamma equal to zeta 2 minus zeta 1 over zeta 2 plus zeta 1. Remember we derived this one for what? Electric field, right? This is electric field, gamma for electric field. The gamma for magnetic field, if you go and derive it yourself, is zeta 1 minus zeta 2 is zeta 1 plus zeta 2. So gamma E is equal to minus gamma H. And that is the reason why electric field go up, electric field go down, electric field go up, electric field go down. It's like that. So you can see that it is electric negative. Alright. Okay, so it just straight away you get the answer, and after that you convert it to instantaneous form. Alright, you convert it to instantaneous form, and there is no problem. Any questions? Any questions? Because once you got the phasor form, I don't think I need to convert into instantaneous form for you, alright? Because this one is quite simple. That means you have two components, and just convert it into two components. Alright? Find the average power density. Okay? Let me see here. Okay, so the instantaneous form has two components also. So you see this one got two components, the instantaneous form will have two components as well. Okay, EE also you have two components, instantaneous form have two components as well. So that one is no issue. Now, the last one, they ask you what is the pointing vector at Z equal to at Z equal to 4 meter. Okay, at Z equal to 4 meter. Okay, what is the average power density at Z equal to 4 meter? So basically, just sub here Z equal to 4. Okay, sub Z equal to 4 inside here, and then find the pointing vector equal to half of real E cross H conjugate. Okay, just substitute inside here. Alright, which is equal to this one. Z equal to 4. Alright. Now, but do you really need to substitute at Z equal to 4? The question why I'm asking you now is, they ask you what is the average power density at Z equal to 4. This is Z less than 0, this is Z greater than 0. Now, in medium 2, it is still a plane wave. A plane wave. A plane wave, and it is a lossless medium. When plane wave and lossless medium, the power density is constant with respect to the direction of propagation. So the power density at Z equal to 4 is the same power density at Z equal to 10, same power density at Z equal to 100, same power density at Z equal to 0.2, same power density at Z equal to 0.
the power density, you can see that, you know, you can substitute Z equal to 4, or you just simply put it as Z equal to 0. So no issue, because the power density is the same at any Z greater than 0, because this is a plane wave. Alright, any questions? Alright, any questions? Alright, remember this is your schedule. If you are interested in how to solve the past year exam questions, 3 year good enough. You need to go all the way to 13. Okay, 3 year good enough. 14, 15, 16, no 17 of course, and 13 is good enough. Okay, so for the next 2 Saturdays, we're going to do the past year question, and you will be at the other side. Alright? And I think I torture you enough. I'm going to torture you one last time. Okay. No lah, no, this one transmission line, not yet. So there's no why are you so happy? We still have 10 minutes. So we go and continue with our transmission line. Okay, transmission line. Where did we left behind? Okay, gentlemen, let's continue. Okay, where did we? Okay. Well, this computer is so slow, right? Go and write to the press and ask the university, go and tell them the university increase the fee, ask them to upgrade the computer, it's so slow. Okay, now, this is the model of the transmission line that we have. Okay, that means you have a series resistance, series inductance, and a parallel conductance, and a parallel admittance. Alright, and under this model, once again, we say that we use KVL and KCL to analyze. Okay, we use KCL to KVL to analyze. So slow. Okay. Now, alright, ladies and gentlemen. Alright. Using KCL, what I have is the current flowing in here will be equal to the current flowing down here plus the current flowing out here. Alright? Now your KVL, okay, will be basically the voltage across here will be equal to the sum of the voltage across here and the sum of voltage across here, right? This voltage plus this voltage is equal to this one. This is your KVL. And the KCL, this current comes in equal to this current goes down and that current goes down. Alright, so this is your KVL and KCL. And we say that, okay, if we apply KVL, alright, we get a single equation up here. Okay, and we divide everything by delta Z. Okay, we arrive at these equations.
Now, if apply KCL, okay, same thing. If I divide everything by delta Z, I get these equations. Now you can see that this del V del Z, this is del I del T, this is del I del Z, this is del V del T. So if we differentiate one more time the two equations, okay, differentiate with respect to Z one more time in the two equations, and we combine the two equations, we arrive at these equations over here. And these equations here, we have d squared v dt squared is equal to gamma squared v, or d squared v dt squared minus gamma v is equal to 0. Sorry, not dz, dz, okay, not dt. Alright, dv squared, dz squared, okay. Now, if we compare our equation with this, you can see that they are of exactly the same form. Because what is del? Del squared. Del squared is actually del squared, del x squared plus del squared, del y squared plus del squared, del z squared. Alright, so it's the same form as that one, exactly the same form. Okay, as long as there is only change in one direction. Okay, transmission is very simple. In electromagnetic field, the wave can propagate in all directions, so you can partial differentiation in 3 directions. But transmission line, it can only go one direction. So, you know, this one go to 0, this one go to 0, and that's what we have over here. Okay, and they are exactly the same thing. So all the equations that we derived previously, okay, with k is equal to beta minus j alpha will be exactly the same. Because gamma squared equal to minus k squared, and now gamma is equal to alpha plus j beta. So basically, a different symbol, but exactly the same equations and exactly the same method of processing. We use k equal to beta minus j alpha in wave propagations. Now we use gamma equal to alpha plus j beta. Okay, alpha plus j beta. Now, the only difference, okay, is that previously when we said k is equal to omega square root of mu epsilon, now we have gamma is equal to this. Gamma equal to this. But is that really any difference? If my gamma equal to R plus j omega L, G plus j omega C, does it really, is that very different? Is that really very different? Can I write it in terms like this, which is equal to omega R over omega plus JL G over omega plus JC can I? So now I have omega there already, right? I have right omega there like that. So if I bring out the J, if I bring out the J, becomes J omega L minus R j omega C minus G j omega no plus
bring the J out. If I bring my J out straight away, from here I say that gamma is equal to JK. Well, so this one here, isn't it the same as the K? Instead of mu epsilon, I have this one. Now, you look at these portions here. Look at these portions here. Remember, if my epsilon is equal to epsilon c, I get epsilon minus sigma over j omega. Somehow I commit an error somewhere, but doesn't matter. No, the error is in the sign, okay? The error is I just suddenly see it. But don't you think that now it's the same? Okay, now it's the same. Alright, now isn't it look like the same form? The same form down here, you put the same form inside here, it is the same form, exactly the same form. But what it means is also that, okay, now not only I change the epsilon to epsilon c, I also change mu to mu c. So basically, it's just the same old form. Okay, so no change at all. We still use the same concept. Okay, that is exactly the same concept. Alright, that is exactly the same concept. Now, my voltage also has a voltage, forward propagating wave, and the backward propagating wave. My current also have a forward propagating wave and backward propagating wave. So same concept. Okay, electric field forward propagating, backward propagating, current also forward propagating, backward propagating. Because why you need a backward propagating? Because transmission line will have a load. A load is just like the boundary. Okay, just now we said the wave propagating hit a boundary. Okay, the boundary can be zeta 2, can be real, can be compressed. So same thing. Now our voltage coming here can hit a load. The load can be real and complex. There will be a reflection. So it's the same concept once again. Alright? Alright? Alright, so now, okay, the ratio between the incident voltage and incident current, which is equal to minus reflected voltage and reflected current. Now, this is once again the same as EI naught over HI naught, which is equal to minus ER naught over HR naught, which is equal to zeta. Remember the same form here, which is the same form here, and zeta, which is equal to square root of mu over epsilon. Now it is also the same form, which is square root of R plus C omega C over G plus C omega C. Alright. And remember, if you cancel J omega from the top and bottom, once again it is like replacing epsilon with an epsilon C. Okay, replacing epsilon with epsilon C and mu by a mu C. So the concept is once again very similar. Alright, I think I'll stop here for today. Okay, and we try to finish this one off next. I try to finish this one off next Tuesday. Alright, ladies and gentlemen, tomorrow if you want to come at room 7, alright? Then we will do the class year questions. May I ask you to go to the website to download all your past year questions to take a look, preferably today. Okay, so tomorrow when we talk about it, you will know what 18, 14, 15. No, sorry. 14, 15, 16. 14, 15, 16. Sem 1 only. Alright, Sem 1 only. Because Sem 2 is taught by different lecturers, then no point. Okay, Sem 1 only. Yes.